differential equations application, population growth and population decay. So we know that the Earth is fairly packed at the moment. There are lots of people on it. So this population growth model can predict to a certain extent the further growth in the population and what's going to happen in the next 20, 30, 40, 100 years. So we have a graph here that you might have seen a graph similar to that. And if we look at around the 1800s, it says there are about 1 billion people on the planet. And then it took just over 120 years for the population to double. Now, if we go up to 1974, then we're at 4 billion people on the planet. And then between 1974 and 2024, which is 50 years, the population doubled. So it took 120 years to go from 1 billion to 2 billion people. And then it only took 50 years to go from 4 billion to 8 billion people. So the population doubling in each case. And the reason for that is basically there are more people on the planet, so there's a greater chance of procreation with people on the planet. And this particular population growth model is the one that's used in the applied maths course. It basically says the rate of change of a population, or the rate of growth of a population, is proportional to the number in the population. More people, more chance for procreation, the growth increases. It's very straightforward. Okay, so the formula that represents it is that, often written as the rate of change of the population is proportional to the number in the population. So that would be dp dt is proportional to p. And then to go from a proportionality to an equal to or an equation, we have to introduce a constant of proportionality, and that's the k value there. So what we're basically saying there is when the population was small, there was a little growth. When the population became larger, the growth in the population became larger. And right now, we're up around the 8 billion region, 9 billion region. And for us to double in population is likely to occur in the next 10 to 15 years. So it's actually very, very quick at this stage. More people in the population, greater population growth. Now let's have a quick look at the k value then. So the k value is a measure of how quickly the population will grow for a particular population size. All right. So if the population is small and the rate of growth is very large, then the k value will be large. If the population is huge and the rate of growth is quite small, then the k value will be quite small. So it's how quickly the population grows for a particular population size. The other thing you might note there is if k is positive, it represents population growth. If k is negative, it represents decay or the dying off of a population. So rather than having that graph that we have where it goes up towards the right, death or decay would be the graph going down towards the right. And again, it curves up in that case, it would curve down in the case of decay. All right, so let's have a look. We have one of the models for population growth that we consider was based on the assumption that the population grows at a rate proportional to the size of the population. That sentence is a sentence that will pop up in the applied maths course. So dp dt is equal to kp. The rate of change of the population growth is proportional to the number in the population. And what we look at in a moment is it a reasonable assumption? And we have an example there, and I'll do a question on a similar one, just so you can see it being done out. So this question is the rate of growth of bacteria in a Petri dish is proportional to the number of bacteria present at any time, approximately. So that tells us our dp dt is proportional to p, so we can use the equation dp dt equals kp. What do we have next? If at the start of an experiment, that's telling me my initial conditions immediately. There are 300 present. So that tells me when t is equal to 0, the population is 300. It's giving me values for my variables in the differential equations at the start of the question. We're also then told, after 1 minute later, there are 3,000 present. So we're given a second set of conditions, and those second set of conditions will allow us to find out what the k value is. So the k value is the constant of proportionality there. And then we're asked to answer the question, how many will be present after 6 minutes, 1 hour, and 24 hours? So the way to do it is to set up our differential equation, put in the initial conditions, and we'll get a formula with k. So first step. So dp dt is equal to kt. Rearrange it. dp over p gives us natural log of P. K times dt gives me kt, and I've got a constant there at the end of it. Fill in my initial conditions. When t is 0, the population is 300. And I've given a subscript there to p, p0. So that's the population at time 0. And you might see this quite a bit. We put the time value as a subscript next to the p, just so we know, or we can keep track of what population we're actually referring to. And when you fill it in, c works out as the natural log of 300. Now, I'd ask you to do this. I've rearranged it, and I've got down in the bottom right hand corner. So pause the video and do it to make sure that I'm right. The population is 300 times e to the power of kt. Now, the next step is to fill in my second set of conditions, and that will allow me to get my k value. So the top box there, what you'll notice is I've put in t is equal to 1. That's 1 minute. And the reason I've put it in is because I don't want the 60 in my power. It just gets really awkward. So I've put in 1 minute, and you just have to remember that this is a tip that you can use, but also in reference to all the times later on, the unit that I'm using is the minute. So when they talk about 1 hour, remember the time will be 60. When we're talking about 24 hours, the time will be 60 by 24. So just bear in mind that we're not dealing in seconds here. So I fill in my second conditions even. P is equal to 300 e to the kt. T is 1. The power or the population should have a subscript of 1 there. There's a misprint. And when you rearrange it, you get k is equal to natural log of 10. So what I then need to do is plug that back into my formula. So the bottom box, P is equal to 300 e to the power of the natural log of 10 all multiplied by t. I've separated out the powers, and e to the power of the natural log of 10 just works out as 10. So the final line there is my formula that relates the population to the time. And now what I can do is use that formula to answer the questions that I'm required to answer. So, answer the questions. So the population at 6 minutes. So we're looking for the population when t is equal to 6. Just put a 6 instead of t, and you'd have to put that into the calculator, get a decimal value, and round it. And actually you'd need to round it down. Also, the unit is bacteria, so there could be 1500 bacteria, because we're looking for the population of bacteria. And number 2, we're looking for the population in 1 hour. So 1 hour is 60 minutes, which is why t is equal to 60. You'd put that in, get a decimal value, and round down, because we're talking about individuals or quantities, and you can't have half of that of a bacteria. And if you get a decimal point, you can't say that there's an extra bacteria created, because it hasn't been created yet. And then for 24 hours, the time is 60 by 24. You can work that out there as well. So we've seen applications of it. You can use it in human populations and obviously bacteria populations based on that example. You can also use it in any animal populations or any animal population. All right. So we go back to the question that they asked before I did it out. And is it a reasonable assumption? So can we make the assumption that the bacteria reproduce indefinitely and at a growth rate which is exponential? Because we did have the population is 300 e to the power of kt. And it's not, right? But it's a simplification and it's a starting point. Other things you need to factor in, and these are just a few of the factors. What are the availability of resources? So what are the nutrients that the bacteria or the humans eat? The proximity to those resources. So some bacteria may be closer to the resources or the food or the nutrients, some may be further away. And that happens with people as well. If there are more resources, we tend to procreate more on average. Are deaths included in the model? They're not. So there's a more complicated model to include the deaths. And what are other factors? So, like I said, this is a simplified model. We don't deal with it in more depth in applied maths, but just bear in mind that there can be more complicated models that will more accurately describe exponential growth and decay for populations. Okay, where is it used? So we've said already that populations are where it's used, human and animal populations, but also the exponential decay or the population decay is used in nuclear decay. And remember there, when it's a decay, that k value works out as negative. Okay, growth of companies. So for example, if a company goes into a town or a city and it does a lot of business, what ends up happening is it can hire more people. If it hires more people, it can produce more stuff. More stuff to sell means more profit. More profit means the business can expand. They can hire more people. So there is a tendency towards exponential growth, I suppose, at the start of the business life in a particular city. And likewise, profit's being made by a company. So if a company makes a lot of profit, it can sell a lot of stuff, it can grow, it can buy more material, it can produce more stuff, it can sell more stuff, so the profit keeps increasing. And again, this is a simplistic model for those. If you're wondering whether this will work for every situation or any situation you're analysing, just ask yourself, will an increase in one quantity lead to a larger rate of increase in the same quantity? And if it will, then you can use dp dt equals k times p.